Hey everyone, in this video we're going to talk about implicit differentiation. And implicit differentiation is what we use when we need to take the derivative of something that's not easily identified as a function of x. So in this case here we have the equation of a circle, x squared plus y squared equals 25. We should know that this is going to be the equation for a circle centered at the origin with a radius of 5. And so even though this here is not a function, doesn't pass the vertical line test, it is differentiable at most points around the circle. In fact, it should be differentiable at every point around the circle except for the x-intercepts, which would be positive 5 and negative 5. Remember, at the x-intercepts, it would have a vertical tangent and therefore would not have a derivative. But let's say we want to find the slope of the tangent line at the point 3, negative 4, which we know will be on this circle because 3 squared plus negative 4 squared would equal 25. In order to do this, we have to treat the function as implicit functions of x. So when we take the derivative of both sides, we're going to take the derivative of every term with respect to x, and we're going to have to use things like the product rule, the quotient rule, the chain rule throughout different functions when we do this. So let's start by saying that we're going to take the derivative of both sides. We're going to take the derivative with respect to x. So d dx of x squared plus d dx of y squared is equal to d dx of 25. Okay? And so really this is going to be step one here, where we're going to differentiate the function both sides with respect to x. All right, so that's what we're doing right now. And so to do that, we're going to take the derivative of x squared. Well, we know that's going to be 2x. The derivative of y squared with respect to x. Now, again, we're treating y as though it's some function of x. So we would have to use the chain rule here, and this would become 2y times whatever the derivative of y is with respect to x. So we're going to say 2y times dy dx. And that's going to equal the derivative of 25, which is just a constant, so that would be 0. The next thing we have to do, okay, we have to collect the terms with dy dx on one side of the equation. So the next piece I have to do is to get the 2y dy dx by itself. So that just means that 2y times dy dx is going to equal a negative 2x. And so that would have been this step 2 right here. We're going to collect the terms dy dx on one side of the equation. I don't have to factor out the dy dx in this case. It's not necessary. So instead, all I'm going to do is divide by 2y on both sides. And what we get is that dy dx is equal to a negative x over y. So if I want to find the derivative of the function, or the slope of this function at any point around the circle, really all I'm going to do is take the opposite of x over y. So if I want to find the derivative at the point 3, 4, or 3, negative 4, I should say, all that means I'm going to get a negative 3 over a negative 4, which becomes a positive 3/4. So that means that the slope of this line right here would just be a positive 3/4. Okay, let's try another example. Here we have what's called a folium. So again, it's not a function, but we can treat it like a differentiable function of x by implicitly taking the derivative. So again, the first step is to differentiate both sides of the function with respect to x. So we're going to take the derivative of x cubed plus the derivative with respect to x of y cubed, and that's going to equal the derivative with respect to x of 9xy. Okay, you'll notice on this side over here I have x times y. I'm going to have to use the product rule over there. Okay, so right here we have d dx of x cubed. That's simply going to be 3x squared. Okay, right here we're taking the derivative with respect to x of y cubed. So again, we're going to have to use the chain rule. So that would be 3y squared times whatever the derivative of y with respect to x is. Again, we're treating y like some differentiable function of x, so d dx. Then on the other side, we have the derivative of 9x. Oops, that's not true. Erase that real quick. We have product rule over here, so we're going to have 9x times the derivative of y plus y times the derivative of 9x. Okay, so again, that's going to give us 3x squared plus 3y squared dy dx, and that's going to equal 9x. The derivative of y with respect to x is just going to be dy dx. All right, derivative of y would just be 1. And then over here we have plus y, and then the derivative of 9x is just going to be times 9. So our next step, we've taken the derivative of both sides now, we need to collect all of our dy dx terms together. I'm going to put those all on the left. I'm going to move the 3x squared over to the right. So that means that we have 3y squared dy dx minus 9x dy dx is equal to 9y minus 3x squared. And so as I look on this left side of the equation here, I can factor out that dy dx. That's our greatest common factor. So this could become dy dx times 3y squared minus 9x, and that's going to equal 9y minus 3x squared. So now the only thing I have to do in order to get the dy dx by itself is to divide by 3y squared minus 9x. So once we do that, our derivative with respect to x is going to equal 9y minus 3x squared divided by 3y squared minus 9x. And if we want to factor out a 3 on the top and bottom, we could make this 3y minus x squared over y squared minus 3x, and that will be fine. That will be our derivative with respect to x. Okay. Try one last example here if we have time. And so here we're looking for the slope of a tangent line to this ellipse right here at the point -1, 2. All right, so here's the equation we have for this ellipse. And again, the steps are, step number 1 is take the derivative with respect to x of each term. So we start with d dx of x squared minus d dx of xy plus d dx of y squared. That's going to equal the derivative with respect to x d dx of 7. Okay, so again, we're going to have to end up using chain rule in the middle right here. Or sorry, not chain rule, but product rule in the middle right here, because that's going to be the product of x times y. So let's start right here with the derivative of x squared. That's simply going to be 2x. Okay, minus, and we have to use the product rule right there. So that's going to be x times the derivative of y with respect to x, so that's going to be dy dx, okay, plus y times the derivative of x, which is simply just going to be 1, plus the derivative of y squared, which is 2y, times the derivative of y with respect to x, which would be dy dx, and that's all going to equal 0. Okay, so what we'll do is we'll distribute our negative right there, and then we're going to collect all of our dy dx terms on the same side. So I'm going to have a negative x dy dx plus 2y dy dx, and that's going to equal, if I subtract over the 2x and add that y over, that's going to be y minus 2x. Same as before, now that I've collected all my terms, I want to make sure that I factor out the dy so I can get it by itself. So dy dx is going to be my common factor here. So we'll just go ahead and say, all right, this is going to be a negative x plus 2y, and that's going to equal y minus 2x. And if we divide both sides, I can say that dy dx is equal to y minus 2x over a negative x plus 2y. Or if you want to rearrange, you could say that y minus 2x is equal to 2y minus x. And if we're looking for the slope of this tangent line, we want to find the slope at the point negative 1, 2. What that's going to equal now is 2 minus 2 times negative 1 over 2 times 2 minus a negative 1. On the top here, we're going to get 2 plus 2 is going to be 4. On the bottom, we're going to get 4 minus a negative 1 is going to be 5. So our slope for this tangent line here is going to be a positive 4/5. Okay. So again, the steps for taking an implicit derivative or implicit differentiation. Step 1 is to take the derivative with respect to x of both sides of the equation. Step 2 is to collect the terms with dy dx on one side of the equation, factor out that dy dx if necessary, and then just solve for dy dx. Okay. I hope these examples give you a good idea of what implicit differentiation is, and I'll see you in the next video.